fermions.
Oh yeah, fermions.
And I'm really excited about this one because these particles are so fundamental.
Yeah.
They're the building blocks of, matter, like everything we see.
Pretty much.
So we've got a ton of research articles and all that lined up that we're going to break down to figure out exactly what fermions are, how they work, how they interact, and I think it's going to be a pretty wild ride.
It really is. They're governed by quantum mechanics, and their behavior is just wild.
Yeah, and that's actually a good point, because I think we should start there. Like, what exactly is a fermion?
At their core, they're defined by their spin.
Okay.
And the spin isn't like, a spinning ball or anything.
Yeah.
It's a purely quantum property.
Right.
It's a type of intrinsic angular momentum that leads to some really, really bizarre behavior.
Bizarre in what way? Can you give me an example?
Well, one of the most significant is the Pauli Exclusion Principle.
Okay, I've heard of that.
Yeah, this principle states that no two identical fermions can occupy the same quantum state at the same time.
Hold on, quantum state.
Yeah.
What is that?
So imagine like a concert,
Okay.
and each seat represents a unique quantum state.
Okay.
So each state has a specific set of quantum numbers,
Uh-huh.
kind of like a row and seat number.
Gotcha.
So the Pauli Exclusion Principle basically says that no two people with the same ticket can occupy the same seat.
Oh, okay, I see.
Yeah.
So it's like a never-ending game of musical chairs where
Yeah.
the music never stops and these fermions can't sit in the same spot.
That's a great way to put it.
I like that.
Yeah. And this rule has some pretty big implications.
Like, what are we talking about here?
Well, for one, it prevents white dwarf stars from collapsing.
Really?
Yeah. White dwarfs are incredibly dense,
Okay.
with electrons all packed together.
Gotcha.
But because electrons are fermions, they can't share the same quantum state.
Uh-huh.
So it's like trying to fit a whole stadium full of people into one elevator.
Right, they're going to be pushing back.
Exactly. So that resistance is what creates degeneracy pressure.
Okay.
And it's strong enough to counteract the inward pull of gravity.
So you're telling me this no two in the same seat rule is literally holding up stars?
Yeah, essentially.
That's incredible.
It is.
So we've talked about the spin and this rule that they have to follow, but are they all the same?
Not at all.
Okay.
In fact, the world of fermions is surprisingly diverse.
Okay.
The standard model of particle physics groups them into two categories: quarks and leptons.
Okay, let's start with quarks. What are those?
Well, they're the only particles that experience all four fundamental forces:
Okay.
strong, weak, electromagnetic, and gravitational.
Wow, so they really experience everything.
They do. Yeah, they're the ultimate team players.
So they must be pretty busy.
They are. They also come in 6 different flavors.
6 flavors?
Yeah, up, down, strange, charm, top, and bottom.
Okay, I'm guessing those aren't like the flavors of ice cream.
No, not at all.
Okay.
And if that wasn't enough, they also have color charge.
Okay, so we're getting a little crazy now. Color charge.
Yeah, so color charge is not like the colors that we see.
Yep.
It's a fundamental property related to the strong force.
Okay.
So each quark carries one of 3 color charges: red, green, or blue.
That is so strange that they call it color.
Oof.
It's like primary colors in painting.
Exactly.
Like you need all 3 to get a neutral color.
You got it.
So are quarks ever found alone, or are they always together?
They're never found alone.
Okay.
They're always bound together in groups called hadrons.
Like protons and neutrons?
Exactly.
Oh, wow.
Protons have 2 up quarks as 1 down quark.
Okay.
And neutrons have 1 up quark and 2 down quarks.
Gotcha.
And because of this color charge, the strong force keeps them glued together.
So they're kind of like the social butterflies of the particle world.
Yeah, you could say that.
What about leptons?
So leptons are more independent.
Okay.
They don't experience the strong interaction, so they exist as free particles.
So no color charges to worry about with these guys?
Nope.
Okay, good.
Yeah. The most familiar lepton is the electron.
Okay.
But it also has heavier cousins, the muon and the tau, each with their corresponding neutrino.
Neutrinos, those are like the ninjas of the particle world, right?
Yeah, they are. They're so hard to detect.
They really are.
Yeah, they interact so weakly with other matter that they can pass through the entire Earth.
Wow. It's amazing how these particles, quarks, and leptons can be so different.
Yeah, it really is.
And you mentioned neutrinos. They can actually change their flavor as they travel.
They can. It's called neutrino oscillation.
So a neutrino that starts as an electron neutrino can just suddenly become a muon neutrino.
Yeah, essentially. And this implies that they actually have a tiny little bit of mass.
Oh, wow.
Which is really crazy.
Yeah, so we've got quarks and leptons,
Mm-hmm.
but are all fermions just these fundamental particles, or can they combine to make something bigger?
That's a great question. And that leads us to the world of composite fermions.
Okay.
Yeah, so even particles made of fermions can behave like a single fermion if they have an odd number of fermionic constituents.
So it's like those Russian nesting dolls.
Yeah, kind of.
But instead of balls, it's just fermions on the way down.
That's a pretty good analogy.
And that really shows how the behavior of these particles applies at different scales.
It does, but to really understand them, we need to go deeper to the level of quantum field theory.
Oh boy, okay, quantum field theory.
Yeah.
That sounds a little intimidating.
It can be, but the core idea is pretty simple.
Okay, good.
So instead of thinking of particles like little marbles bouncing around,
Okay.
imagine them as excitations of quantum fields that permeate all of space.
Okay, so the universe is like a giant ocean.
Yeah,
And the particles are like waves.
exactly.
So instead of a universe full of tiny billiard balls, we have this ocean of fields.
Right.
And waves are the particles.
Yeah, and just like ocean waves can be different sizes,
Mm-hmm.
the excitations in these fields correspond to different types of particles.
Okay.
So fermions with their unique half-integer spin are described by the Dirac equation.
Okay, the Dirac equation, that sounds intense.
Yeah, it's a bit mathematically complex.
So do I need a PhD to understand this?
No, not at all.
Okay, good.
What's important is that it doesn't just describe their behavior, it actually predicted the existence of antimatter.
Antimatter? You mean like that stuff they use in sci-fi to power spaceships?
Kinda, yeah. So every fermion has a corresponding antiparticle with the same mass but opposite charge.
So they all have like evil twins.
Yeah, you could say that.
So what happens when they meet? Do they explode?
Kind of. They annihilate each other,
Oh, wow.
releasing a burst of energy.
Okay, so they can't exist in the same place at the same time.
Exactly.
Okay, so back to the Dirac equation.
Yeah.
It also tells us about fermions and relativity, right?
It does. It reveals that fermions are inherently relativistic particles.
So Einstein's ideas about warped space-time
Mm-hmm.
are tied to fermions.
They are.
Wow, they're a lot more complicated than I thought.
They really are.
Okay, so we've got fermions as excitations in quantum fields, and they have to follow the laws of relativity.
Right.
How do they actually interact with each other in this quantum world?
That's where second quantization comes in.
Second quantization.
Yeah. So in quantum field theory, particles can be created and destroyed
Okay.
by operators acting on these fields.
Hmm.
It's like the fields have little switches that turn particles on and off.
So it's like whack-a-mole with particles.
Kind of, yeah.
Okay, I like that.
And for fermions, there's a specific rule called anti-commutation.
Anti-commutation, does that have to do with the no two in the same seat rule?
It does.
Okay.
It basically means that the order you apply these creation and annihilation operators matters.
Okay.
So you can't create two identical fermions in the same state.
So the Pauli Exclusion Principle is built into these fields.
Exactly.
That's incredible.
It is.
So can we step back and talk about how they interact in the real world?
Sure. One of the most striking examples is the diversity of materials we see around us.
What do you mean?
So metals, insulators, semiconductors,
Okay.
their properties are dictated by the behavior of electrons.
Which are fermions.
Right.
So the reason a copper wire conducts electricity
Yeah.
and wood doesn't
Yeah.
is because of how their electrons are behaving.
Exactly.
That's so cool.
It is. And then you have semiconductors,
Right.
which have a unique structure that allows them to conduct electricity only under certain conditions.
So that's what makes them important for electronics, right?
Exactly.
They're like little goat keepers,
Yeah.
controlling the flow of electricity.
It's amazing that the entire digital age is built upon the behavior of fermions.
That is wild. What other cool stuff can they do?
Well, there's superconductivity,
Okay.
where materials at really low temperatures can conduct electricity with zero resistance.
Oh, wow.
So imagine power lines that don't lose energy.
That would be incredible.
It would.
How did they do that?
Well, it's thanks to Cooper pairs, which are two electrons acting as one.
Wait, two electrons can act as one?
They can, at these low temperatures, they can overcome their repulsion
Uh-huh.
and form these bound pairs.
Okay.
And because a Cooper pair has an integer spin, it acts like a boson.
So they're breaking the rules.
Kind of, yeah. They're teaming up to become something else.
Oh, wow. I like that.
And this allows them to condense into a single quantum state,
Okay.
leading to superconductivity.
They're sneaky.
They are.
Okay, what other surprises are there?
Well, there's also the fractional quantum Hall effect.
Okay.
This happens in two-dimensional electron systems when you expose them to magnetic fields,
Okay.
and it leads to quantized electrical conductance.
Quantized conductance.
Yeah, so the current can only flow in specific steps.
So that's another only in the quantum world kind of thing.
It is. And what's really fascinating is that it's explained by quasi-particles called anyons.
Anyons.
Yeah, and they have fractional charge
Okay.
and statistics that are neither fermionic nor bosonic.
So it's like a whole other universe.
It really is. And studying fermions under these conditions
Yeah.
has really given us a much deeper understanding of quantum matter,
Okay.
It's even led to new applications like topological quantum computing.
Wow. Okay, so we've covered a lot.
Yeah, we have.
From the basic nature of fermions to their role in material,
Oh.
and now these mind-bending mysteries.
Yeah.
And we haven't even talked about supersymmetry or sterile neutrinos.
Right.
We'll have to dive into that in the next part.
Definitely. It's going to be a wild ride.
It is.
The world of fermions is full of surprises.
It really is.
So many secrets left to be revealed.
Okay, well, everyone, thanks for joining us for this deep dive on fermions. We'll be back soon with part 2.
See you then. So we were talking about composite fermions.
Right, those Russian nesting dolls.
Yeah, exactly.
Fermions all the way down.
But to really understand how weird these particles are,
Okay.
we need to talk about quantum field theory.
Quantum field theory. Okay.
It sounds complicated, but it's a very elegant idea.
Okay, good.
So instead of particles being like little marbles,
Right.
they're like excitations in quantum fields that permeate all of space.
Okay, so the universe is like an ocean.
Yeah.
And particles are like the waves.
Exactly. Okay, I like that. And fermions, with their half-integer spin, are described by the Dirac equation.
The Dirac equation.
It's a bit mathy.
Yeah.
But what's important is that it predicted antimatter.
Antimatter. Like in Star Trek?
Yeah, kind of. So every fermion has an antiparticle with the same mass,
Okay.
but opposite charge.
So like evil twins.
Yeah, essentially.
What happens when they meet?
They annihilate each other,
Oh, wow.
releasing a burst of energy.
Okay, so they can't exist in the same place.
Exactly.
So the Dirac equation also tells us about relativity, right?
Right. It shows that fermions are inherently relativity.
So Einstein's ideas about space and time
Yeah.
are connected to fermions.
They are.
Wow. Okay, so how do these particles actually interact with each other?
That's where second quantization comes in.
Second quantization. What is that?
So particles can be created and destroyed. By operators acting on these fields,
Okay.
it's like they have little switches that can turn on and off particles.
So it's like a game of whack-a-mole with particles popping in and
And
out.
for fermions, they have to follow anti-commutation.
Anti-commutation, what's that?
It means the order you create and destroy them matters.
Okay.
You can't just create two identical fermions in the same state.
So the Pauli Exclusion Principle is built into the fields.
Exactly.
Wow, that's pretty amazing.
It is. So let's talk about how this all plays out in the real world.
Okay, yeah, let's get concrete.
Think about all the different types of materials around us.
Okay, like what?
Metals, insulators, semiconductors.
Right.
Their properties are determined by electron behavior,
Which are fermions.
right?
So that's why a copper wire conducts electricity.
Yeah.
But wood doesn't.
Exactly.
It all comes down to the electrons.
And then you have semiconductors.
Okay.
They can conduct electricity, but only under certain conditions.
Yeah, that's why they're so important for electronics.
Exactly. They're like tiny gatekeepers.
Controlling the flow of information.
It's amazing to think that the digital age is built on the behavior of fermions.
Yeah, that's pretty wild. What else can they do?
Well, there's superconductivity.
Superconductivity.
Yeah. At very low temperatures, some materials can conduct electricity with no resistance.
Wow, that's pretty amazing.
Imagine power lines with no energy loss.
That would be a game changer.
It would?
How is that even possible?
It's because of something called Cooper pairs.
Cooper pairs.
Yeah, basically two electrons acting as one.
Wait, so two electrons can act like one particle?
They can at these low temperatures.
Okay.
They form these bound pairs.
So they're kind of cheating the system
You could say that.
to become something else.
And because they have integer spin, they act like bosons,
Okay, so they're not fermions anymore.
not as a pair.
That's pretty sneaky.
And this bosonic behavior allows them to condense into a single quantum state.
And that's what leads to superconductivity.
Exactly.
Wow, okay. What other weird things are there?
Well, there's the fractional quantum Hall effect.
Okay.
This happens when you expose 2D electron systems to magnetic fields,
Okay.
and it leads to quantized conductance.
Quantized conductance. What does that even mean?
It means the current can only flow in specific steps.
Okay, so only in the quantum world.
Right. And what's really cool is that it's explained by quasi-particles called anyons.
Anyons.
Yeah, and they have fractional charge.
Fractional charge.
Yeah, and they're neither fermions nor bosons.
Okay, my head is starting to spin.
It's a lot to take in.
But this is all so fascinating.
It is. And studying fermions in these extreme conditions has really helped us understand quantum matter.
Okay.
It's even opened up new areas like topological quantum computing.
Wow. Okay, so we've gone from the basics of fermions
Yeah.
to how they behave in materials
Right.
to these really weird quantum effects.
And we haven't even talked about supersymmetry or sterile neutrinos.
Yeah, we'll have to save that for next time.
Definitely. Those are some really mind-blowing ideas.
Okay, well, everyone, thanks for sticking with us. We'll be back soon with the final part of our deep dive on fermions.
See you then.
Welcome back, everyone, to the final part of our Fermion deep dive. Are you ready to get into some of the biggest mysteries in particle physics?
Absolutely. It's time to explore the unknown.
Let's talk about supersymmetry. It sounds like something out of a comic book. Every particle has a secret twin.
Yeah, it's a pretty wild idea. Supersymmetry, or SUSY, says that every fermion has a partner boson and vice versa.
So every particle has a dance partner, but they're doing completely different moves.
Exactly. But if these superpartners exist, why haven't we seen them?
Yeah, where are they hiding?
Well, we think they're much heavier than the regular particles.
So we need more powerful experiments to find them.
Right, the Large Hadron Collider is looking for them.
Okay, and if we find them, what would that mean?
It would be huge. It would be revolutionize our understanding of physics.
In what way?
Well, it could solve some big problems like the hierarchy problem.
The hierarchy problem.
It asks why the weak force is so much stronger than gravity.
Okay.
Like why an ant can lift so much more than an elephant.
Yeah, that's a good analogy.
So supersymmetry could explain why the forces are so different.
Okay, so it could explain why the universe is the way it is.
It could, but we're still looking for evidence. What about sterile neutrinos?
Yeah, you mentioned them before. They sound pretty mysterious.
They're these hypothetical particles that only interact through gravity.
So they're like ghosts.
Yeah, they'd pass through everything.
But how would we even know they're there?
There are some hints in neutrino oscillation experiments.
Okay, what kind of hints?
Well, sometimes neutrinos change flavor in a way that suggests sterile neutrinos might exist.
So something weird is happening that we can't explain.
Yeah, it's like seeing ripples in a pond and wondering if there's an invisible duck swimming underneath.
Okay, that's a good way to put it. So why else are sterile neutrinos so exciting?
Because they could be dark matter.
Dark matter.
Yeah, we know it makes up a lot of the universe, but we don't know what it is.
Right, it's invisible.
Exactly. But sterile neutrinos could be a perfect candidate.
Wow, so these ghost particles could be the answer to one of the biggest mysteries in cosmology.
It's definitely a possibility. It shows how important fermions are.
Yeah, we started with the basics of fermions, then how they work in materials,
Right.
and now these crazy mysteries that could change everything we know.
It's been quite a journey.
It has. So what's the big takeaway for our listeners? Why should we care about these particles?
Because fermions are the foundation of reality.
Really?
Yeah, they make up the atoms in our bodies, the stars in the sky, even dark matter.
It's like realizing the whole universe is built on these tiny particles.
And the more we learn about them, the more we understand about the universe.
Yeah, that's a good point. As we wrap up, what's something you want our listeners to think about?
What's that?
Well, next time you look around at the world, remember that everything is made of these tiny particles with their crazy rules, and there's still so much we don't know.
Yeah, who knows what other secrets are out there.
That's what makes it so exciting. Thanks for joining us for this deep dive into the world of fermions.
It's been a pleasure. Until next time, keep exploring.